Hello, everyone. This is me, Billy Younger, again for www.youtube.com/Billy with a capital B, Younger with a capital Y, Physics with a capital P, Solutions with a capital first S. I am here today. I'm going to solve another Gauss's law style problem. This time it's a non-conducting sphere whose charge is distributed uniformly throughout. This one I'm sort of doing as if you're already somewhat familiar with it. If you happen to not be that familiar with it, I recommend you first go and see the video I have called Conducting Spheres Electric Field Determined Using Gauss's Law. A good first Gauss's Law example. That's the whole title. And I put it in that title specifically so you guys would understand that that's probably the first one for you to watch. You'll notice because of that, it actually takes, it's actually like 38 minutes long, but I'm really explaining a lot of the details of what's going on. This one, I will still be explaining details, but I'll be rapidly firing through it a little easier. A little quicker, so you'll see more like what you do when you try to use Gauss's law in this way. Specifically in this physics class, one of the major ways you use Gauss's law is by attempting to extract the electric field from within the integrand of a surface integral equation. So you've got a surface integral equal to Q over epsilon naught, where Q is the enclosed charge, and you're trying to extract the electric field using symmetries and what you knew about electric fields from your experience with Coulomb's law. So anyways, let me start by sharing the screen so you'll see exactly what problem we're doing. The problem we're doing is this one. It says a non-conducting sphere. I say that specifically because conducting sphere, automatically the charges are all just going to disperse out to the outer surface. But a non-conducting sphere of radius r and total charge q has a uniform charge density of rho equals a constant. That rho is what we normally call charge per unit volume. Sometimes books will write it dq over dv, where v is volume. In this case, you're saying it's a constant, meaning if you took out a 1 millimeter by 1 millimeter by 1 millimeter segment, found out how much charge is on it, any other 1 millimeter by 1 millimeter by 1 millimeter segment would have exactly the same amount of charge. Part A, we're wanting to compute the electric field caused by the sphere for r less than the actual radius of the sphere, and in part B, we're going to do it for r greater than the radius of the sphere. Note, if the sphere center is at the origin, which is what I'm going to do, then r is the spherical coordinate. R is the spherical coordinate r, which is always the distance from the origin. It also has a unit vector r hat that at any point points away from the origin, but along the connecting along the line connecting the point to the origin. In other words, I'm going to be making use of some of the information about spherical coordinates. I put a link to that in that other video I just mentioned to you about a conducting sphere. So again, if any of that worries you, you're not sure you know anything about spherical coordinates or about the symbols I'll be using, the symbols is the only reason I'm using these coordinates. You don't really have to know that much about them except for these symbols exist. But again, if you have any problem with that, then by all means, switch and watch the 38-minute video on conducting sphere. All right, I'm going to stop sharing the screen, and then I'm going to start sharing the screen with my open notes. So now I'm sharing the screen. I've already sort of rewritten the problem in cursive. That doesn't bother anybody, but I would like to see people would be able to write in cursive again, because really writing in print is way less efficient and way slower. So anyways, it says a non-conducting sphere of radius capital R and total charge Q distributed uniformly throughout the sphere. Calculate the electric field everywhere. So let's get started. I'm going to say my solution. So the solution. The first thing we've got to do is we got to realize that Gauss's law says the closed integral of E dotted with dA is equal to the total charge enclosed within that closed surface that you're integrating over, divided by epsilon naught. I am going to draw a coordinate system like such. And hopefully I can move that line just a little bit. Okay, so there's my coordinate system. And in fact, this will be my z-axis, this will be my x-axis, and this will be my y-axis. Now the trick, remember, for Gauss's law is we're trying to solve for that little e that's in the integrand. In order to do that, we've got to have certain symmetries that allow the electric field to be everywhere, either constant on the surface of some made-up surface we call the Gaussian surface, or parallel to the vector dA on that surface, or the opposite, which is the electric field is actually perpendicular or zero even on those other surfaces. So at the end, the left-hand side should always be the electric field times some area. In some cases, we'll just call the area A. In other cases, we'll say, okay, well, this is a sphere, so the area is 4 pi r squared. Or we'll say, okay, this is the surface of a soup can, but only the surface part where the soup label is, in which case the area is 2 pi r times the height or something like that. So that's always what the left-hand side is supposed to be. We're going to use the fact that Coulomb's law is a spherically symmetric law, and it does give us, in fact, the electric field as well as the force. So the electric field depends on the electric field depends on the charge causing the electric field directly. So if you double the charge, you double the electric field. But it also is inversely proportional to the square of the distance between that charge and where you are. So if you take any sphere centered on that charge, the electric field will be a constant on it. So that's sort of the symmetry we're making use of. So let me first draw the actual sphere, and I think I'll draw the sphere in a nice color green. Actually, let me cheat a little bit and let the computer actually make my sphere a better sphere. So that turned out actually pretty good, not too bad. If anything, I'd maybe move it down just a tad. Oh, no, not that far. That looks about right there. No, it's about right there. Okay, so that's our actual sphere, and it has a radius r, and it has a radius big R and a total charge Q, but that's distributed uniformly throughout. So first off, we're going to do part one, which is R less than big R. In other words, we're going to imagine being inside of the sphere and hopefully try to figure out what the charge of the sphere is. Imagine the sphere being inside of the sphere, and then try to compute what fraction of the total charge Q is inside of there. So I'm going to draw my Gaussian surface. This time it's going to be a sphere as well, because I realize the hypothesis that I'm going to make, which I'll put right here. The hypothesis I'm going to make is because of the spherical symmetry of the charge distribution, I expect the electric field is going to be equal to some magnitude that depends only on r, and it's going to point radially outward, just like the r hat vector from spherical coordinates. So there's my hypothesis. Now I know if I draw a sphere centered on the center of the sphere, then the dA vector will all be r hats as well, so that the E and the dA are always parallel. So that's exactly what we want, the kind of symmetry we want. We want either the E and the dA to be parallel, or we want the electric field to be a constant on the actual dA surface, and the dA vector, of course, is perpendicular to that. So they're actually one and the same statement, even though they sound like two different ones. Or finally, we want the electric field to be perpendicular to the dA, so that it will actually cancel out. So now I can go ahead and do my left-hand side once I draw my Gaussian surface. So my Gaussian surface for this one, actually, I'm going to make use of the wonderful features of electronics and try to do a good sphere. Okay, this sphere has a radius little r, which actually I tried to draw there. and that R obviously is less than big R. And in fact, it has a little differential area element, which looks like that. You can imagine the lines going back to the origin. And this bottom edge, of course, has a very specific length, and the left and right edge has a very specific length. So dA is actually going to be equal to some dA R hat. That's the important thing. If you're doing double integrals, you could actually come up with a nice double integral version of what that differential area element is, but that's the whole point. We don't want to do that. Okay, we're using symmetries to rid us of all that crap. So now I can write out the left-hand side of Gauss's law. Left-hand side says the closed integral of E dot dA. So that's going to become integral E of R hat dotted with dA R hat, which you already know just becomes E of R times 4 pi R squared. Again, because the E of R comes, well, let me write that a little bigger. I'm not happy with that being on that edge like that. We know that's going to become, I'll go ahead and show the extra step this time, E of R, because you're integrating it over the Gaussian surface. And this is the Gaussian surface. Okay, because you're integrating it over the Gaussian surface, it's a fixed radius R, so you end up getting the integral of dA. Oops, I don't want to write that in red. You get the integral of dA, which is just the surface area of the spherical surface, and then R hat dot R hat, which we've already decided was 1. So in this case, you get E of R times 4 pi R squared. That's it. That's the left-hand side. Now, here's the hard part. The right-hand side, there's a couple ways you can do it. I'm going to do it the way with the least math, but I'll sort of spell out how you could do it with the math if you wanted. So if you wanted to do it with the math, you could say that I know Q, the total charge, is equal to the integral of rho dV. And since it's uniformly distributed, that rho can just come out in front, and I get the integral of dV. Excuse me. The integral of dV, which obviously becomes rho times 4/3 pi little r cubed, because we're only talking about Q enclosed, and for r less than r, the Q enclosed only goes out to a radius r. But since it's uniformly distributed, we already know that rho is going to be equal to Q over 4/3, which will make the 4 in the bottom and the 3 on top, pi r cubed. So we know that's actually what the constant rho is, and I can plug that in. So we could go through that integral and do all that by, and I would use, for instance, a dV, which would be 4 pi r squared dr, which I've made arguments for on my YouTube channel of showing you why it's that instead of really being like 4/3 pi pi 4/3 pi parenthesis r plus dr close parenthesis cubed minus 4/3 pi r cubed. I've made arguments why that's not the case. It works out just fine to be calling it 4 pi r squared dr. But either way, that gets it for you is by doing that integral r. Now, the other neat thing is because rho is a constant, we can say since rho equals a constant, we know that Q times 3 over 4 pi r cubed, which is equal to rho, is also equal to 3 times Q enclosed over 4 pi times little r cubed. So with that in mind, we can figure out that Q enclosed with no calculus whatsoever is, in fact, once I mark out all the stuff, there's a 3 that marks out there, there's a 4 pi that marks out there. Let's do it with an X since I missed it a little bit. And then all you're left with is Q enclosed is equal to Q oops, wrong color, is equal to Q times R over big R quantity cubed. And that's exactly right. That's perfectly fine. So again, you could have done that integral, or you can just do this. Most people will do this. Later, I'll do one where we sort of have to do the integral. There's probably ways to avoid that too, but I'm just going to do the integral on a different example. So now we're going to say the right-hand side of Gauss's law, which is Q enclosed over epsilon naught. We know that's going to equal 1 over epsilon naught times Q times R cubed over big R cubed. So now we can set left-hand side equal to right-hand side. And when we do that, we get E of R times 4 pi R squared is equal to Q over epsilon naught times R cubed over R cubed. Now, what happens here is you can see that two of these exponents, namely the R2, the R squared and the R cubed, those two disappear and leave just R to the 1 power by canceling out all these. So ultimately what we get is E is equal to Q over 4 pi epsilon naught R cubed times R to the 1 power, and then all that times R hat, and that's for R less than big R. So that's part of our quest, was determining what the electric field was for R less than big R. Now for R greater than big R, it really should be trivial. So let's do part 2 now. Part 2, which is R greater than big R. We know the left-hand, the same hypothesis. Okay, so we know the left-hand side is going to be equal to the closed integral of E dot dA. And that's going to be, of course, E of R times 4 pi R squared. Again, I'm doing it fast like we would in an actual exam. I know that's what it's going to work out to be. We do the right-hand side. The right-hand side, of course, is equal to Q enclosed over epsilon naught. Well, guess what? My Gaussian surface that I'm considering now is actually this Gaussian surface, like so, whose radius is R greater than big R. Okay, so I know for a fact that the charge enclosed is all of the charge Q, so it's just Q, excuse me, change color again. It's just Q over epsilon naught. So in this case, we get E is equal to Q over 4 pi epsilon naught R squared R hat. So in fact, we can write our electric field E as a piecewise function. And the piecewise function is Q over 4 pi epsilon naught R cubed times R hat for R less than or equal to big R. If you'll notice, it actually turns out to be the same thing when R equals big R. That's why I made it continuous now and said less than or equal to. And it equals Q over 4 pi epsilon naught R squared R hat. That's an R squared there. And that's for R greater than or equal to big R. And in fact, if we were to make a quick graph of its magnitude, it would be actually quite easy. Let's do that for a second. I'm going to just make this like the y-axis and this like the r-axis. So this will actually be the electric field. And for the distance r, basically what we see is the electric field is going to be linearly related to the radius. So it's going to look just like this. And it goes through the origin. And this value is Q over 4 pi epsilon naught big R squared. And then from there on out, it falls off like 1 over R squared. So that's what the magnitude of this electric field looks like. Notice there is no discontinuity like there was in the problem that I suggested you see first before you see this one. And that's because there's no surface charge density. So that's it. That's a nice application of Gauss's law in such a way that we use it to extract the electric field out of the integrand. And we now have a solution. And I hope that helps. Have a good one. Tell a friend.